my name is Maria Masri. It's a pleasure to be part of the DATAPLAT workshop. Today I'll be presenting our work entitled RTGEN, a relative temporal graph generator, authored by Sultan Miklos, Philippe Répin, Pierre Meillet, and myself. This work is a collaboration between Orange Labs and the University of Rennes 1 France. In this work, we are interested in datasets that are used to evaluate the performance of graph-oriented data platforms. Now, real-world graphs, however, are either not publicly available or do not fit the scale requirement. Hence, practitioners tend to generate synthetic graphs whose characteristics mimic those of real-world graphs. Most real-world graphs are dynamic, meaning that edges and vertices can leave or join the graph at any time instant. Examples of such graphs are transportation, citation, and sensor networks. Now, analyzing the history of such graphs allows the detection of anomalies or forecasting future behavior. Hence, a recent interest has been steered towards managing temporal graphs and thus generating synthetic temporal graphs, which constitutes the main motivation of this work. Now, here's the outline of the presentation. First, I'll present the related work and its limitation. Second, I'll provide the preliminaries needed to describe key concepts of our proposal. Third, I will provide an overview of RTGEN, our proposed temporal graph generator. After the overview, I will describe more deeply the proposed graph generation model. Then I will present and discuss the evaluation results of RTGEN. Finally, I will conclude the work and provide a future perspective. An extensive work has been posited for the generation of random graphs that mimic the characteristics of real-world graphs. Two key features of such graph generators are the degree distribution and the community structure. However, the generation of temporal graphs has received much less attention. Now, available temporal graph generators are either growth only or only produce simple edge updates, such as flipping the direction of edges. Now, besides, none of the proposed solutions controls the evolution of the degree distribution of synthetic graphs and the community structure, which are two essential key features that should be addressed by temporal graph generators. This limitation motivated us to propose and implement RTGEN, standing for Relative Temporal Graph Generator. Now, what's the degree of a vertex? The degree is equal to the number of edges connected to that vertex, whereas the degree distribution is the probability distribution of the entire graph. The Jean-Claude model consists of generating random graphs by assigning each vertex with a desired degree distribution. Now, for a sufficiently large number of added edges, the obtained degree of each vertex approximates the desired degree. Now, let's define the communities. The community can be intuitively defined as a group of vertices that are more densely connected between each other than they are with the rest of the graph. The stochastic block model is used to generate random graphs with any given expected community structure. This is done by setting a stochastic community matrix that defines the between and within communities' linkage probabilities. After a sufficiently large number of added edges, the community density matrix of the obtained graph approximates the given one. Inspired by the Jean-Claude model and stochastic block model, we proposed RTGEN. As an input, RTGEN takes the parameters of the evolution of the degree distribution, the number of vertices and snapshots, and stochastic community matrix, and generates a sequence of graphs whose degree distribution approximates the given ground truth parameters. Our mechanism is based on a relative generation procedure consisting of generating a graph snapshot, for example, GI, from a graph snapshot GI-1 by applying a number of graph updates. These graph updates can be either an edge insertion or deletion or a vertex addition. To be able to generate a graph GI with a desired degree distribution Phi by applying a sequence of graph updates to graph snapshot GI-1 having degree distribution Phi-1, we need to find a mapping between both degree distributions. Now, dynamic graphs tend to gradually evolve. Hence, we need to use an optimal solver to be able to generate the graph snapshot GI-1 from GI by applying the minimum number of graph updates. On the right side illustration below, we can derive that 50 nodes having a degree 30 in graph snapshot GI-1 should have a degree 40 in the newly created graph snapshot GI. Hence, a degree variation equal to 10. Now, to be able to control both the evolution of the degree distribution and community matrix, we changed the original Chang-Gross linkage probability that is equal to the degree of the vertex to the total number of degrees in the graph. The first modification consists of replacing the desired degree distribution with a degree variation to account for the evolution of the degree distribution. And the second modification consists of adding the probability of adding an edge to a vertex belonging to a given community. With the obtained formula, we were able to produce a series of random graphs with a given evolution of the degree distribution and a community structure. To facilitate setting the parameters of the stochastic community matrix, we defined an auto-filling procedure, which produces the stochastic community matrix of a hierarchical tree using only two user-defined parameters, the height, h, and the branching factor b of the tree. We further define a user parameter k that is proportional to the difference between the between and within community linkage probabilities. And this parameter will be further discussed in the evaluation section. To evaluate RTGEN, we produced several graphs and visualized the obtained degree distribution. In the set of input parameters A, we produced the growth-only graphs, but in the parameters B, we produced graphs presenting a peak in the mean degree over time. Now, in both generated graphs, we are only considering a Gaussian degree distribution. However, RTGEN is also capable of producing any given degree distribution, such as power law degree distributions. Now, to evaluate the community-aware feature of RTGEN, we applied a community detection algorithm and visualized the obtained graphs. It's clear that the graph indeed presents a hierarchical community structure. Besides, increasing the value of parameter k, as previously mentioned, increases the difference between the within and between community edge densities. Now, from the right-hand plot, we can conclude that the value of the modularity, that is a metric used to quantitatively measure the strength of the community structure of the graph, also increases with the increase of k. In this presentation, we introduced a temporal graph generator that is capable of generating a sequence of graph snapshots with a given degree distribution and a community structure. RTGEN can be used to assess the performance of graph-oriented data platforms. As a future perspective, we're planning to generate graphs with a dynamic community structure by adding community splits, merges, growth, and shrinks. Thank you for your attention.